So binomial distributions is another distribution that we're going to look at. And we've done kind of some things with binomial distributions. We just didn't talk about binomial distributions. So this is going to take us a little bit back to some probabilities. We have to learn some new probabilities to do this. So first, we're going to determine whether a random variable is considered a binomial. So binomial by means two. So we're dealing with something that really has like two options to it, which is why it's a binomial. So your favorite restaurant is giving away a coupon with every purchase of a meal. 20% of the coupons entitle you to a free milkshake, and the rest say better luck next time. So I have two things that can happen here. I either can win a free milkshake or I win nothing. So two events that can occur. Suppose that 10 of you order lunches at the restaurant. We want to know what is the probability that 3 of you will win a free milkshake. So if 3 of you win, what would that probability be? This is not a straightforward probability. It depends on the fact that there are different ways to get 3 winners from a group of 10. So this goes back to those combinations that we had. So there are several different combinations of 3 out of 10 that could occur. So the probability isn't as straightforward as, like everybody has 20%, like you have everybody's 20%, that's part of it. But then there's, like I said, several ways that event can occur. So in general, if we let X be the number of people out of 10 that win a free milkshake, we will learn that X has a distribution called a binomial distribution, which is one of the most useful binomial distributions. So we actually use this one quite a bit, regardless of whether we know that we're doing it. In the example just described, each time we examine a coupon, it is called a trial. So there was 10 trials because we had 10 people that went in and bought tickets. When a coupon is good for a free milkshake, it is called a success. And when it wasn't, then we call that a fail. So one of the things you have to learn with binomial distributions is your success is not always going to be like the positive event, it's the event that we're interested in happening. So a success is only when the event we're recording happens. Or assessing. Let's use a different word that. So this is when the event we'll say investigating. That sounds better. So don't always think that success is always the positive event. I could be interested in what's the probability that 8 of my 10 friends don't win a coupon. And in that case, losing is the success, if that is what I'm interested in. So success is just whatever is the part that we're investigating, that we're trying to record. So the probability X represents the number of successes in 10 trials. A random variable that represents the number of successes in a series of trials has a probability distribution called a binomial distribution. So what we're talking about is when we have random variables that can either succeed or fail. So we have those two options. That's when we have a binomial distribution. So for a binomial distribution, a fixed number of trials are conducted. So it's not for any number of trials, we have it fixed. So we look at binomial distribution for only 10 trials or only 20 trials or only 25 trials. It's got a set number of trials that we look at. There are 2 possible outcomes for each trial. One is labeled success, the other is labeled a failure. So that's what I'm talking about, the 2 outcomes. This is what makes it binomial. The probability of success is the same in each trial, so it doesn't change from trial to trial. So as far as like the coupons go, each person, when they grab a coupon, should have the same probability of winning. Now, if you're talking about drawing cards without replacement, then each time you draw a card, the probability of the next card changes. So that is when we don't have the probability of success would be the same on each trial. The trials are independent. That means that the outcome of one trial does not affect the outcome of another trial. And the random variable X represents the number of successes that occur. So our random variable is always going to be successes. So X is the random variable, is the number of successes in N trials. So that is our random variable that we are recording, is just those X's. Okay, so just decide whether these are going to be we can do a binomial experiment in these cases. So we want to decide in each case whether X is a binomial random variable. So a coin is tossed 10 times. We let X be the number of times the coin lands heads. So what we have is two things can happen. We can have a head, which is a success. We can have a tail, which is the thing we're not looking for. That is going to be what we consider a fail. So we have two options, success or fail. The probability should not change between each coin flip. We also have a fixed number of trials. And like I said, probability of heads is the same for each flip. And also each flip is independent. The probability of what I get on that coin does not affect the other one. So as we see here, this is a binomial experiment. Each toss of the coin is a trial. There are two possible outcomes. X represents the number of heads. The heads count as success. The trials are independent. So in that case, the trials are just those coin flips. Toss of a coin is a trial. Here we got 5 basketball players. Each attempt a free throw. X would be the number of free throws made. So we do have a fixed number. We do have a success and a fail. The problem is that, like each player has a different probability of making a free throw. So I think if anybody's watched basketball, you notice that there's certain players that were always excited to get to do a free throw because they're more likely to make it, and the ones are not. Like if I remember correctly, they never wanted Shaquille O'Neal to do free throws because he wasn't particularly great at it. So his probability would be different from a different player. So there may be another player that was really good at free throws. I believe, I'm trying to remember what his name. I'll say Richard Hamilton, I think is what his name was. I think he was really good at free throws. That's all back a long time ago. That was the Pistons. But like I said, each player has a different probability. So this means that the probability of success is different from player to player. This is not a binomial experiment. Next one, 10 cards are in a box. So we have a fixed number of trials. Again, we have 10. 5 are red and 5 are green. 3 of the cards are drawn at random. Let X be the number of red cards drawn. So in this case, it's not really explicit here, but we are assuming that each time we draw a card, it affects the probability of the next card. Because we're drawing 3 cards. So if I draw 1 card, that means the next one's probability has changed. So drawing each card affects the probability of the next card. So that right there, that is enough to say that the events are not independent. This is not a binomial experiment. So just certain things we have to look for. So we just need to, like I said, make sure that we have a fixed number of trials, that we have 2 options that we're going to come out. We're going to have a success and a fail. So here we have a success and fail, like, red could be, would be our success, green would be our fail, and the last one. If I had like red cards, green cards, and blue cards, then we'd have 3 different events. That wouldn't be binomial. So like I said, we need those 2 events. We need to make sure the probability of each event stays the same. So like different players are going to have different probabilities of making free throws. So that doesn't fit. However, each time I flip a coin, that probability stays the same. And then the other part, which kind of goes with that part about having the same probability for each trial. If the events aren't independent, that also causes the probability of each trial to be different. So it has to be independent trials as well for this to work. So we want to decide in each case whether X is a binomial random variable. So we got a fair die is rolled 20 times. We let X be the number of times the die comes up 6. Then we have a standard deck of 52 cards, contains 4 aces. The 4 cards are dealt without replacement from the deck. Let X be the number of aces. And then we have a simple random variable of 50 voters is drawn from the residents in a large city. Let X be the number who plan to vote for a position to increase spending on public schools. All right, so this first one, if we roll a 20-sided die, our trials are independent. So we're going to roll this die 20 times. Okay, yeah, trials are independent. We have the probability is the same for each trial. Oops, second. All right, sorry, something was happening there. And then we also have 2 choices. So our success, that's when we get a 6. Every time we get a fail, that's when we roll anything that's not a 6. So we have a fixed number of trials, we have a success and we have a fail. The probability stays the same on each trial, and each trial is independent. This can be modeled with a binomial random variable. A standard deck of 52 cards contains 4 aces. The 4 cards are dealt without replacement from the deck. So we let X be the number of aces. So if we have no replacement, that means that the trials are not independent. What we're going to see here is that each time I draw a card, each draw affects the probability of the next draw. So this it's not a binomial variable. Binomial random variable. And then this last one, so we have a fixed number of trials again, this a simple random sample of 50 voters, so 50 trials is drawn from the residents of the city. Let X be the number who plan to vote for a position to increase spending on the public schools. So if we think about this, we don't really have like 2 options. We could have people are going to vote yes. We have people who vote no. And then we have people who are not going to pick either. So we might have 50 trials, but we can't really say how many are going to be yeses necessarily. Okay. And also the other problem is that each person who votes, the probability of what they're going to vote for changes too. So the probability of each voter, which is my trials, so once again, it's not the same each time. I don't have a voter and there's like a 50% chance they're going to vote yes and 50% chance they're going to vote no each time. Each one varies. If like they may not know what they're going to pick right until they get there, and they start deciding, their other political values, like whether they're Democrat or Republican or independent, that will affect those probabilities. So my probabilities are not the same in each trial. And you can argue that it really isn't two choices, though we could kind of force it.